Welcome to the video on Digital CMOS VLSI Circuits, Course 20 EC 214, offered by the Department of Electronics and Communication Engineering at Sri Ramakrishna Engineering College. In this slide, we see the complete representation of the Gajski Y-Chart. The diagram is divided into three major domains: the structural domain on the left, the behavioral domain on the right, and the geometrical or physical domain at the bottom. These three domains represent three different perspectives of VLSI system design. Let us start with the behavioral domain. In the behavioral domain, we describe what the system does. At the highest level, the system is represented as an algorithm. The algorithm defines the logical sequence of operations required to solve a problem. Next, the algorithm is refined into a finite state machine or functional description. Further refinement leads to Boolean equations. Thus, the behavioral domain moves from high-level description to logic-level description. Now let us move to the structural domain. In the structural domain, we describe how the system is constructed using hardware components. Boolean equations are implemented using logic gates. These logic gates form larger components such as registers and arithmetic logic units. Multiple components combine to form a processor. Thus, this domain focuses on interconnection of components and hierarchy. Now let us examine the physical or geometrical domain. In this domain, the structural components are translated into physical layout. Transistors are arranged to form logic gates. Logic gates are implemented using mask patterns. Cells are placed on the chip using cell placement techniques. Modules are arranged during module placement. Then chip floor planning determines approximate block locations. Finally, the complete layout is fabricated using mask layers. The concentric circles indicate levels of abstraction. At the outermost circle, we have the highest abstraction, such as algorithm. As we move inward, the design becomes more refined and closer to silicon implementation. Thus, the Gajski Y-Chart shows how a VLSI system moves from behavior to structure, and finally to physical realization. It is a powerful framework that helps engineers manage complexity in modern CMOS VLSI design. In this slide, we clearly see that the Gajski Y-Chart consists of three major domains: the behavioral domain, the structural domain, and the physical domain. Each domain represents a different abstraction level in VLSI design. Let us briefly understand them. The behavioral domain describes what the system does. It focuses on algorithms, functional descriptions, and logic behavior. The structural domain describes how the system is built using hardware components such as logic gates, registers, and processors. The physical domain describes where and how the system is implemented on silicon. Now let us focus on the physical or geometry domain in detail. In modern VLSI systems, we cannot directly place a very large system on a chip. Therefore, the first step is physical partitioning. In physical partitioning, the large system is subdivided into smaller ASIC-sized pieces. This helps in managing complexity and improving layout efficiency. After partitioning, these small blocks are arranged together in the form of clusters. Clustering groups related modules so that communication delay and routing complexity are reduced. The next important step is floor planning. In floor planning, we determine the approximate location of each module or block on the chip. This stage gives a high-level geometric view of the chip layout. It ensures optimal area utilization and reduced interconnection delay. After floor planning, we move to module layout and cell layout. In module layout, each block is designed with detailed geometry. In cell layout, transistors and logic gates are precisely arranged. Finally, the blocks are placed on the chip, and interconnections between cells and blocks are defined carefully. This step ensures that the design is ready for fabrication. Thus, the physical domain transforms abstract logic into real silicon implementation. Understanding these steps is very important because improper physical design can increase delay, power consumption, and chip area. Therefore, the physical domain plays a critical role in CMOS VLSI design. In this slide, we focus on two important domains of the Gajski Y-Chart: the behavioral domain and the structural domain. Let us first understand the behavioral domain. The behavioral domain describes what the system does. At this level, the circuit is modeled using procedural code, which represents the design at a higher level of abstraction. In simple terms, we describe the functionality without worrying about how the hardware is built. The first hierarchy in the behavioral domain is the system level. At the system level, the overall behavior of the architecture is defined. For example, if we are designing a processor, we define what operations it must perform, such as addition, subtraction, or logical operations. The next stage involves defining a set of algorithms. Algorithms specify how the system processes different parameters. Flowcharts may also be used to describe control flow and data movement. After the algorithm level, we move to the RTL level. RTL stands for Register Transfer Level. At this stage, coding is done using hardware description languages such as Verilog or VHDL. Here, we describe how data moves between registers and how operations occur on clock edges. After RTL, we move toward the logic level. At the logic level, the system is expressed in terms of zeros and ones. Boolean expressions are defined, and the transfer function of the circuit becomes clear. Thus, the behavioral domain moves from abstract system description to logic representation. Now let us move to the structural domain. While the behavioral domain focuses on what the system does, the structural domain focuses on how the system is constructed. In this domain, particular blocks are connected using sets of signals or netlists. A netlist defines how different components are interconnected. For example, logic gates are connected to form functional blocks. Functional blocks are connected to form modules. Modules are combined to form larger subsystems. Here, we are more interested in the hardware structure rather than abstract functionality. Thus, the structural domain describes the interconnection of components. In summary, the behavioral domain defines functionality. The structural domain defines hardware organization. Both domains are interconnected. Behavior determines structure, and structure enables implementation. Understanding these two domains is essential before moving into physical layout and fabrication stages. Thank you for watching this video on digital CMOS VLSI circuits.